All right, so here's number 14. Use Kepler's third law to determine the period of a comet in years whose orbit extends to 50,500 astronomical units, which is within um, the inner Oort cloud, just to let you know, um, which is the outermost part of the solar system, and then gets as close as point 0.5 astronomical units at closest approach to the sun. Express your answer in scientific notation and round two places past the decimal. All right, so let's write out Kepler's third law, of course, and there's the answer. It's 4.01 million years, 4.01 times 10 to the 6 years. All right, so Kepler's third law looks like this. A cubed, the semi-major axis cubed, is equal to p squared. All right, that's supposed to be squared. All right, so A has to be in astronomical units and P has to be in years. And so well, we don't have A, but we have two numbers here. We've got the furthest the object is and the closest it is. And so we just take the average of the two values, right? Because that's really what the semi-major axis is. All right, so A turns out to be 50,500 plus 0.5, and then you divide that by 2. All right, so here, let's get our calculator and do this. All right, so 50,500 plus 0.5 equals, all right, and then divide that by 2. So this is our, that's our semi-major axis, right? So, uh, so it's 25,000, 25,250.5, 25,250.5, all right, AU. All right, and then of course we use the modified version of Kepler's third law, and we're going to solve for p. So p, of course, is going to be the square root of 25,250.5. But of course, I've got to cube that, all right, and then take the square root. All right, so here we go. All right, there's my calculator. All right, so that number's already in my calculator. So I just raise it to the third power equals, and then take the cube, the square root. All right, and so and there it is, right? So here's the number. There's the decimal between the 7 and the 3 right there. So it's 1, 2, 3, 1, 2, 3. Okay, so it's 4.01 times 10 to the 6th. All right, so 4.01 times 10 to the 6th years. So, a little more than 4 million years. All right, so here's number 15. It says, given the temperature of a body decreases as the square root of the distance from the sun, is as the square root as the distance increases from the sun, estimate the temperature of a comet nucleus in the Kuiper belt. Remember, that's beyond the orbit of Neptune, at a distance of 43.6 astronomical units from the sun. Take the temperature at 1 AU, that's the distance that the Earth is from the sun, to be 300 Kelvin. We're going to round to one place past the decimal. All right, so here's the equation that we use. T2, so it's this equation right here. T2 is equal to T1 times the square root of R1 over R2. And of course, the temperature has to be in Kelvin. They give us that the temperature for the Earth is at the temperature that the Earth receives from the sun is 300 Kelvin, and R1 is, of course, 1 astronomical unit. All right, so here we go. Let's put the numbers in. So T2, this is for this comet, is going to equal 300 Kelvin. All right, times the square root of 1 astronomical unit divided by 43.6. 43.6 astronomical unit. And of course the AU's cancel. And so this will give us a temperature, the temperature of the comet that is 43.6 astronomical units away from the sun. That's actually beyond the orbit of Pluto, just to let you know. Pluto's at about 40 astronomical units away. All right, so here we go. All right, let me move this so you guys can see the calculation a little bit better. Oops, geez, I didn't mean to do that. All right, so there it is. All right, so here we go. All right, so it's going to be 300 times the with this calculator, it's a little. Let me do it in a little different order. All right, so it's going to be 1 divided by 43.6. All right, so that's underneath the radical right there. With this calculator, you got to do it. It's better to do it in this order. All right, so oh no, that's not the way. Let me clear that again. All right, so 1 divided by 43.6 equals, all right, so it's a really small number. I take the square root of that, all right, and then multiply that times 300. So times 300. All right, and so this gives me, so it's 45.43. So they want us to round one place past the decimal. Since the 3 is less than 5, I don't round the 4 up. So it's going to be 45.4 Kelvin. All right, remember, in Blackboard, you just enter the numerical value. So that was number 15. So here's number 16. Calculate the kinetic energy of impact of a 15,000 kilogram object hitting the Earth, like a comet or an asteroid or something like that, that is hitting the Earth at 40 kilometers per second. Express your answer in kilotons of TNT. Use the conversion that 1 kiloton is 4 times 10 to the 12th joules. Joules are units of energy that we use in physics all the time. Anyhow, be sure to convert kilometers per second to meters per second. All right, so, and there's the answer. It turns out to be about 3 kilotons. All right, so here's the equation. This thing called kinetic energy, the energy of motion, is, so that's generally we use KE for kinetic energy in physics, is 1/2 the mass times the velocity squared. All right, so that's the equation for kinetic energy. The mass has to be in kilograms. So mass, these are the units, has to be in kilograms. But the velocity has to be in meters per second, not kilometers per second. So that's really all you have to change, because this is the impactor, whatever it is that's hitting the Earth, is 15,000 kilograms. So that's we don't have to change the units there. But the velocity we have to change the units. But that's pretty easy to do. So the velocity turns out to be 40 kilometers per second. So 40 kilometers per second. And of course, I know that in 1 kilometer, there are 1,000 meters, right? Or 10 to the third is the same thing. So this becomes, 40,000. Right? Just put 3 more zeros, meters per second. All right, so now we're ready to go. And so the kinetic energy, which by the way, the kinetic energy is going to give us, when you have the mass in kilograms and the velocity in meters per second and you square it, that gives you joules of energy. All right, so anyhow, it's 1/2. Our mass is 15,000. All right, and then our velocity turns out to be 40,000 meters per second, but we've got to square that. All right, so again, this answer will be in joules, and then we'll convert that to kilotons. All right, so here's our calculator. All right, let's clear that. All right, so here we go. So I'm going to start with the 40,000. All right, square that times 15,000. And then divide by 2. I mean, I didn't have to do it in that order. All right, but so anyhow, so the decimal place would be right over here. So it's 1, 2, 3. So there's 6, 9, 12. So it would be 1.2. So it's the answer is 1.2 1.2 times 10 to the 13th joules. And so it turns out that, and we're going to use this conversion right here, 1 kiloton. So like if you had 1,000 tons of TNT, this unit was used a lot during World War II. So 1 kiloton of TNT, I'm not going to write the of TNT, is the equivalent of 4 times 10 to the 12th joules. Right, so the joules cancel, and so I just take that number that's already in my calculator and divide it by 12. I divide it by 4 times 10 to the 12th. So divided by 4 times 10 to the 12th equals, all right? And so that's how you get 3, right, which is what we predicted already. So that tells us that this thing, so this, this would be the amount of energy in joules. So 1.2 times 10 to the 13th joules, but that turns out to be 3 kilotons of TNT. All right, so that is problem number 16.